So I wanted to start this video that I'm going to help you with some page 9 stuff by repeating my instructions that I'd really encourage you to write this little note about what each of these points are somewhere either on those page 8 notes or here at the side on the page 9 stuff we're going to be working on. I would recommend you not write this graph on this graph itself. Draw your own little kind of example exactly like what I have it here and just make a note about what each of these points represents so that you can analyze different looking graphs in order to find those answers. So just a general hill diagram. Make sure you're starting higher than you're lower for this example here. And these A, B, C, D, E points are really important that we can find them on that graph. And just like I said in my video, the beginning energy at the very, very far left is always the energy of the reactants. At the very, very far right, that energy E is the energy of the products, just like we normally see a reaction going from reactants to products, left to right normally. And then the only other real solid point that we need to be able to find and use is called the activated complex. And that is the total energy at the top of that peak, always going to be in the middle of our graph. These other points, B and D, what we call activation energy. And these, notice, don't go all the way down to that x-axis because these are the difference between two of these 3 points we've already talked about. Activation energy is always the difference between that activated complex and the reactant energy. And D is what we call the enthalpy, the change in energy of our reaction. We always subtract the products minus reactants, just like we've done multiple times earlier in this unit. So please take a second to write these down someplace on page 8 or 9 because you need to be able to find these key points. And this is exactly what we're going to be doing with the page 9 problems. So here on page 9, we're going to be talking about the forward reaction. And I'm going to use red in order to remind ourselves that the reactants are at the far left of the forward reaction, products are at the right, and activated complexes at the top. So if I ask you about the energy of the reactants, well, the energy, if we follow that over to the y-axis, is 80. The energy of the products is 160. And the activated complex is about 240. So these are the 3 points that we just need to be able to find on the graph and follow over to the y-axis in order to get them filled in. And then to calculate the activation energy, remember this is the activated complex minus the reactants. So this is 240 minus 80, which is 160. Our enthalpy value is products minus reactants. So that's going to be 160 minus 80, which is 80. Now, either because this is a positive 80 here, or because you can see that we are increasing in energy as we go from reactants to products, which must mean we're taking in some energy, this is going to be an endothermic reaction. Now, when we flip things to the reverse reaction, I'm going to use purple here to show this difference. The reverse reaction is going in the opposite direction. So the thing we're starting with, our reactants for the reverse reaction, are where our old products were. And our products of the reverse reaction are where the reactants used to be in the forward reaction. We're just flipping those two around. It's important to realize that the activated complex stays in the exact same spot. It does not move at all. So here the energy of our reactants of the reverse reaction is 160. The products are 80, but the activated complex is still 240. So here when we're trying to find our activation energy of the reverse reaction, we're still doing activated complex minus reactants, but because my reactants are now 160, when I'm doing 240 minus 160, now this activation energy is 80. It's smaller for the reverse reaction, but you can even see that the hill looks smaller from the reverse reaction side than it did when we were moving forward. This is a much bigger looking hill here, a lot higher energy to climb to get that reaction started. And then our enthalpy, which is always products minus reactants, because we've switched those reactants, now we're doing 80 minus 160, which gets us a negative 80. We flip the direction of the reaction, and just like in Hess's law, we flip the sign of that enthalpy value. So either because this is a negative value, or because as we're going from reactants to products, this time we're going down in energy, then you should be able to tell that this is an exothermic reaction. Energy is being released from this reaction. So we're going to ask you to do questions like page 9 on your test. You're not going to have to do quite the same amount of work as I'm asking you to do on page 10 when you're on your test, but this is a good way to practice problem solving and showing you understand what each of those values are and how they relate to each other on page 10. So the first problem is pretty straightforward. Just remember that this EA thing that we're asking for is our activation energy. They say activation energy. They do EA as like energy of activation, but that's all that we're asking for there. And then this comes back to the podcast stuff. Draw how a catalyst would affect the energy of our reaction. And I'm going to help you out with that here using a dotted line. What we said in that podcast is that it lowers our activation energy when we add a catalyst. And you know that makes it go faster. But literally what that does is just lower this hill. That way the activation energy, the energy to get activated, is going to be lower because that activated complex is lower. So it's just a smaller hill, helps us go faster. That's all that you need to draw is a little curved line lowering that hill. Keep in mind that the reactant and product energy do not change, just the hill in between. Now, to help you out with questions 2 and 3, I would recommend that you copy down 7 lines onto the first graph y-axis and go by 50s up to 350 because we can see that our highest energy, the peak of this second graph, is going to be at 350. And on this third graph, since our peak, the highest point on our graph, is going to be about 220, let's go by 50s up to 250. So 5 lines, number them this way, and that's going to help keep your graph a little bit more consistent. It's not important. This is 220, so somewhere in between that 250 and that 200, maybe a little bit lower than that. But it doesn't have to be perfect and exact. I just want you to practice making the general correct shape of these graphs from the numbers that you already have here. So do your best. I'll help you out with these when I get back if you need, or come in for tutorials.